Now we're going to take a look at a different concept, but it also involves infinity. And remember what we said about infinity, it's the concept that something is getting arbitrarily large, and not just in a positive way, but it could be in a negative way. So something that for us, real numbers that are very, very big, but either positive or negative. Now, when we looked at infinite limits, this was the scenario. Our value, our independent variable x, was approaching a fixed number, but then we observed that the y value, or function value, just got bigger and bigger and bigger, and again, either a positive or a negative way. So now we're going to ask ourselves this question. So let y equals f of x. So we have our function, right? What happens to y as x now becomes very, very large in a positive or negative way? So if we were to, for instance, evaluate our function at bigger and bigger values of x, what would happen to the y? Would the y values just continue to get bigger and bigger, or, in a positive or negative way? Or would the y values get closer and closer to a fixed number? That's what the concept of limits at infinity is all about, right? So if y equals f of x approaches a fixed number, and as we did before, let's call that fixed number L, L for limit. So if your function approaches this fixed number whenever x gets sufficiently large or arbitrarily large, let's just say sufficiently large. So whenever x gets sufficiently large, and again, it could be either positive or negative, right? So really we're talking about the magnitude, right? So large positive or large negative numbers of x. So if your function value approaches a fixed number whenever that happens, we say that f of x has a limit, which would be L, right, at infinity. So it's like we're kind of saying, like, what happens, to our y values if we go to the far never regions of our number line, right? And then how do we denote this? Well, it's still the idea that our function value or y value is approaching a fixed number, so we're going to still use our limit notation. But now what changes is this: when we look at what x is approaching, see, this is saying that x is getting sufficiently large, really, really large, and we can make it as large as we want by either going to positive infinity or negative infinity. So now what you're going to see is here, you're going to have that, and then f of x is still there, and we would say, if, when we look at the process of evaluating this, if the process produces a fixed number, in other words, our function approaches a fixed number as x gets very, very large, either plus or minus, then we still refer to that as our limit, right? So again, to emphasize the difference here, it's the fact that we're now letting our independent variable x get very, very large, and then we're going to have to determine what happens to our value of the function, or y values, right? Now, in terms of those three methods that we've looked at, the numerical, the graphical, and the algebraic, I'll briefly mention all three. We're going to spend a significant amount of time on the algebraic piece, but the numerical and the graphical, again, they kind of give you a good kind of intro to the idea. It helps you, especially the graphical approach, helps you visualize what's going on. And in fact, maybe that would be a good way to start. So I'm going to sketch a graph and see and use a particular concept to illustrate this idea of a limit at infinity, right? So let's start with the graphical approach. And what would it look like for a function to have a limit at infinity? Now, again, in terms of the number line, if your x is going to plus or minus infinity, that means, we have our negative infinity is far to the left on the horizontal axis, and then positive infinity is far to the right on our horizontal axis. So it's basically saying we would have to look in these regions of the graph and to see if the y value is approaching a fixed number. But the idea of trying to use this finite space, this little graph that these axes that I've drawn here, to try to use something like that to convey, okay, x is getting larger and larger either this way or this way without bound, is not really complete. So again, we're just gonna try to be able to read the graph and assume that the indicated patterns were to continue. All right, so I'm going to draw. First thing I'm going to draw are some horizontal lines. So I'm going to draw a horizontal line there. And let's say that this corresponds to a y value of 2. So this would be the line y equals 2. And let me draw another horizontal line. Let's say down here, and then maybe this corresponds to like -4, right? And now I'm going to draw the graph of my function. So I'm going to draw a portion of it going to the right, and then another portion going to the left. So let's say in fact, let me start down here. So let's say that the graph is something like this. And then up, and then it's doing that, right? So let's say that's the graph of our function, right? So this is y equals f of x. And based on this graph, I would like to answer these two questions. What is the limit as x goes to positive infinity of this function, right? We'll figure that out. And then let me say, well, what is the limit as x goes to negative infinity of my function, right? Well, positive infinity, right? So x going to positive infinity means you look far to the right. Look far to the right on your graph, right? Because that's the direction that indicates that your x value is getting very, very large in a positive way. Well, if let's say I start at the origin. I start at 0, and then to go to positive infinity, I'd have to go this way, right? And I would have to keep going as far as I could to the right, right? So it doesn't matter really any of these values. It's essentially like you're trying to get to the end of the curve. And based on this pattern here, look at what the graph is doing. So as you go further and further to the right, the y value is approaching a value of 2. So your function has a limit of 2 as x goes to positive infinity, right? What about if we go to negative infinity? So again, let's say I start at the y-intercept here when x is equal to 0. Now to go to negative infinity, I have to go far to the left. So if I go to the left, I'm on the graph, and I keep going, and I keep going, and I keep going. And again, based on the pattern in the graph, right? Again, we kind of infer certain patterns based on how we read graphs, it appears that as x goes far to the left, right, then our y value approaches -4, right? So that is what we would state is our limit at -infinity. So this would have a value of -4. So again, whenever your x is going to -infinity, what you would look far to the left, right? And again, there would have to be some pattern in the graph. Now, if there is no pattern, then there's a way we would answer that, right? But if you notice how I started by drawing, after I drew the x and y axes, I drew these two horizontal lines. Well, it turns out that when the function has a limit at infinity, so like it approaches a fixed number, so going far to the right, the function approaches 2. Going far to the left, the function approaches -4. Well, when your function approaches those fixed constants, it ends up graphically meaning that the function has a horizontal asymptote, right? It's approaching, it's going either far to the right and to the left, and it's kind of leveling off at a fixed number. It doesn't keep oscillating. The graph doesn't go off to infinity. What it's doing, it's leveling off at a fixed constant, and that fixed constant corresponds to a horizontal asymptote, right? So what we could say here in my particular graph, right? So I'll just say when a limit at infinity exists, right? And it could be either one. It doesn't have to be both all the time. It could be in just one direction. But whenever in one of these directions, far to the right, far to the left, if your function approaches a fixed value, so when a limit at infinity exists, the function has a horizontal asymptote at the line y equal L. So whatever that limit value is. So the function has a horizontal asymptote at y equals L. Or you could say of y equals L. So remember, just a quick reminder, when the function has an infinite limit, so when the y value goes off to infinity, that corresponds to a vertical asymptote. Now we're saying if x is going to plus or minus infinity and the y value is approaching a constant, then that constant corresponds to a horizontal asymptote. So, when you in general, when you think about asymptotes, vertical and horizontal, infinity plays a big role. It's just a matter of, is it the y value that's going to infinity, or is it the x value that's going to infinity to cause that particular feature of the graph or of the function, right? So that's what it looks like now graphically. Now, what if there is no nice constant leveling off of the function, right? So here are a couple more examples, and for this I'll draw some specific type of functions. So let's say we have y equals x squared. So I'm going to take our standard parabola. It goes like this, right? And so what this means is just by thinking about y equals x squared, no matter how far I go to the right or to the left, the parabola, in this case, because it opens upwards, the y value just keeps getting bigger and bigger, right? Because remember, in terms of the y-axis, positive infinities in that direction, negative infinities in that direction. In fact, let me go ahead and label everything here, right? This is in terms of x, this is in terms of y. So what could we say about y equals x squared? Well, as x goes to positive infinity, x squared also goes to positive infinity. That would be this part of the graph, right? Right here. So that's this. In fact, what I will do, let me color code it, right? That's what this arrow is saying, is no matter how far to the right you go, your y value is just going to get even bigger. And that kind of makes sense. If you think about it, think about what your function is doing. You're squaring a number. Well, if you take a very big number and square it, you'll get an even bigger number. And the same thing happens as you go in the negative direction. So as x goes to negative infinity, what happens to x squared? Well, because you're squaring the number, you're going to get a positive y value. And if it's already big, right, it will become, again, even bigger. So as far as where would you look on the graph to make this conclusion? Well, it's over here, right? X going to negative infinity means I have to go far to the left on the x-axis. Then I have to look at what portion of the graph corresponds to that, and that portion, again, the y value just keeps getting bigger and bigger and bigger in a positive way, right? So sometimes you have some simple functions that you just don't have that nice leveling off, right? I'll do another example here. What if we change the power from a square, from a 2 to a 3? What if we make it y equals x cubed? Again, you might remember the graph of y equals x cubed. It looks like this. Again, let me label things. So positive infinity there, negative infinity there, positive there, and then negative there. Now, if I were to ask myself the same two questions, what happens to y equals x cubed as x goes to positive infinity? Well, I think we know what portion of the graph to look at now. So as x goes to positive infinity, x cubed gets even bigger. It's the same idea. You know, it's going to be, if you take a large positive number and raise it to the third power, you're going to get an even larger positive number, right? And again, you could specify it with the positive sign there. And that portion of the graph, again, like this one, would correspond to this, right? And then what happens as x? Now, this is where there's a slight difference between the parabola and the cubic function. If we look at the limit as x approaches negative infinity of x cubed, well, the thing is, if I take a negative number and raise it to the third power, because that power is odd, I am going to get a negative answer. And that's why you have this portion of the graph now going down. And let me write the answer first. So this would, here, as x goes to negative infinity, x cubed goes to negative infinity. And as far as where it corresponds on the graph, it's that part that corresponds to that concept, right? So graphically, you know, fairly straightforward. You don't always have a limit at infinity in terms of there's not always a nice leveling off. Sometimes you can have functions that go off to positive infinity or negative infinity, right? And our goal eventually will be able to determine those properties using only algebra. So like if the function is a lot more complicated than just an x squared, where we might not be able to generate the graph easily, or we might not be given the graph, right? And you're asked to evaluate the limit algebraically, we will have to establish some techniques to do that, right? Now, so that's the graphical approach. What does it look like numerically? Again, it's not something that we focus heavily on, but I will mention it just for completeness. And in some sense, what does it mean to like estimate a limit at infinity numerically? Well, I'll give you a table with just a few values. So let's say you have your f and your x values, your x and y values. Now, to estimate or to simulate the process of x going to positive infinity, you'd have to now start putting larger and larger values of x into your function. Probably one of the best ways to do that is to do like powers of 10. So 10, and I'll write them as 10 squared instead of having to write a whole bunch of zeros, and then 10 cubed, and then 10 to the fourth, and I'll just stop at 10 to the fifth. So this pattern here, as x is just getting bigger and bigger and bigger, this is what you would use as an example of your x value going to positive infinity. And then if the function does have a limit as x goes to positive infinity, we would expect to see the y values getting closer and closer to a number. So maybe something like 4.7120, and then 4.8914, and then 4.9001, 4.9907, and 4.9999. If we saw something like this, then based on this table, we could say that numerically it appears that as x approaches positive infinity, this function, whatever it is, it's getting closer and closer to 5. And then right away we can conclude that y equals 5 is a horizontal asymptote, right? So very easily we can say quite a bit by this particular table, right? And in order to simulate like a limit as x goes to negative infinity, all I'd have to do is just put a negative sign in front of those powers of 10, right? So again, I'll just kind of state that a sequence such as, and I'll just kind of write it like if it looks like this, like negative 10. Now I'm kind of writing it in the opposite direction. Actually, let me do this. And I'll put a whole bunch of negative 10s, and then I'll go back and put the powers. So now squared, cubed, fourth, and to the fifth. So again, this way now, a sequence that looks like this simulates or approximates this type of limit as x goes to negative infinity. And what you would do, you would take your function, evaluate it at these, again look at the pattern and see if there is a y value that that a y value that's being approached. Now, part of the issue with doing limits numerically is that oftentimes you might think, well, let me just plug one big number in and just say, oh, this looks like 5, so I'm going to say it's 5. The problem with some functions, what if that function oscillates? What if it's a function that has a trigonometric component to it that causes some oscillation? And you just happen to, pick a value of x that gives you this particular number. But then maybe someone else would pick like 10 to the 6th and then maybe get a negative 3.8 or something like that. So you have to be careful when you're doing this sort of numerical approximation. You have to look at your function carefully and see, does it have any kind of component that would make it oscillate? Because if it does, if there is oscillation there, depending on the type of oscillation, the limit might not exist. right? In fact, to illustrate that, let me jump back to the graphical approach and show you what it means as far as you can have one type of oscillation where you don't have a limit at infinity, but then you could have another type where you do. So for instance, if you take your sine function, so here's the sine graph, and I'm just going to do it for positive values of x. It looks like this. And then it continues that periodic property all the way to the right. So your y values are never approaching a fixed value, right? So if y equals sine of x, right, then the limit as x approaches positive infinity of this function does not exist, right? So it does not exist, right? However, if you take a function like this one, if you take y equals sine of x, if you take your sine function but then divide it by x, it turns out that this particular function, as x gets very, very large, it approaches 0. It does this. So it now this one at x equals 0, if we had a limit of this as x approaches 0, it's not undefined. It turns out it has a limit of 1. That fact will actually be proven at a later date. But it starts out here, and it does oscillate, but what it does, every time it oscillates, the amplitude gets smaller and smaller and smaller until it's just kind of, it's almost like it's converging, it's getting closer and closer to the y, to the x-axis. And that x-axis becomes, now it's not a horizontal asymptote per se, it's because it's kind of oscillating like this. So you do have to be careful. Again, when you're using a numerical approach, a function like this might give you the wrong impression that there is a limit if you just plug in a fixed number, but you have to say, well, what happens if that pattern continues, right? This one, I'll go ahead and say, so then your limit as x approaches positive infinity of this is 0, right? So be careful. The numerical approach, the graphical approach, they're good intuitive methods to kind of give you a feel of what's going on. But it's not until you really look at the algebraic approach that you get a very good sense of the limit at infinity. And that is what we're going to look at in the next video.